All right, let's get started. Welcome everyone, and go ahead and grab a seat. I am absolutely thrilled to welcome you to today's Masterclass Explainer. Today, we're unlocking nothing less than the language of the universe. If you've ever found yourself totally overwhelmed by a physics or astronomy textbook just because the numbers look like giant barcodes of zeros, well, you're in exactly the right place. We're going to break down exactly how scientists communicate these massive, extreme scales. So I want to kick things off by posing a question to all of you. How do we actually measure the universe? I mean, from the absolutely massive scale of the cosmos all the way down to the tiny, tiny quantum realm without literally running out of chalkboard space. Think about it for a second. Physical reality is so incredibly vast and yet simultaneously so microscopic that our standard, everyday way of writing numbers just completely breaks down when we try to capture it.
So here's the game plan for today's syllabus. We'll start by looking at the problem of scale, then we'll define what scientific notation actually is. After that, we'll go over the golden rules, and finally, we'll put it all into practice with adding and subtracting, and then multiplying and dividing. Quick and easy.
All right, let's dive right into Section 1, the problem of scale and visualizing the impossible. Before we get into the solution, we really need to wrap our heads around the pure frustration of dealing with these massive, unwieldy quantities. Just take a look at this number, 138 million kilometers. Look at the sheer volume of zeros trailing at the end there. Now, for context, this is the average distance from the Earth to the Sun. Imagine having to write that out over and over again in a complex physics equation. It takes up way too much space, it's incredibly tough to read at a glance, and honestly, it's just a recipe for a calculation disaster. You're practically guaranteed to miss a zero at some point and totally wreck your entire equation. And you know, the problem definitely doesn't go away when we zoom in either. Let's scale all the way down to the micro level. This ridiculous string of zeros right here, that represents the diameter of a single hydrogen atom in meters. It just goes to show that incredibly tiny numbers are just as painful to read, write, and visualize as the massive ones. I mean, trying to count those decimal places with the naked eye is just a nightmare. There's got to be a better way. And thankfully, there is. So let's move right into Section 2. What is scientific notation? The ultimate time-saving tool. Here's the formal definition. Scientific notation is essentially a shorthand way of representing very large or very small numbers, expressing their decimal places conveniently as powers of 10. By using these powers of 10, we're basically compressing all those empty, space-hogging zeros into a neat, tiny little package. It makes dealing with these extreme physical sizes actually manageable. Now, I want you to notice the strict mathematical boundary we have to follow with this. The numerical part at the front, the base number, must always be written as a number from 1 to 9. It can't be 0.5, and it definitely can't be 15. It has to be a single non-zero digit sitting right to the left of the decimal point. And then, that single-digit number is multiplied by a whole number power of 10. That's the core structure. So, how do we actually build this? Well, that brings us to Section 3, the golden rules, or how to construct the notation. Grab your notebooks, class, because we're going to walk through the exact step-by-step mechanics of constructing these numbers. Okay, here's the core 3-step algorithm you absolutely need to memorize. Think of this as your fail-proof checklist. Step 1. You take your messy number and you move the decimal point until only one non-zero digit remains on the left side. Step 2. You carefully count the number of places that decimal point just moved. And Step 3. You use that exact count as the power or exponent of 10. That's it. 1, 2, 3. Let's actually see those exact steps in action using our earlier examples. We'll compare macro versus micro. Looking at the macro scale on the left, for the sun's distance, we grab that hidden decimal at the very end of the zeros and we move it all the way to the left 8 places, until it sits directly after the 1. Now because we move to the left, our exponent is positive, so 138 million elegantly becomes 1.38 times 10 to the power of 8. Now check out the micro scale on the right. For the atom's diameter, we move the decimal to the right, skipping over 11 zeros until it lands right after the 5. And because we move to the right to represent a tiny, tiny number, our exponent becomes negative. We end up with 5.2 times 10 to the power of negative 11. So remember, left is positive, right is negative. All right, now that your foundation is perfectly set, I'm going to challenge the class to actually use these tools. Let's move to Section 4, adding and subtracting, which really comes down to the rule of matching powers. Let's walk through this addition problem together. Look at the equation here.
We're trying to add 5.123 times 10 to the fourth to 3.28 times 10 to the fifth. Now, the absolute most crucial point here is this. You cannot just add these base numbers together right out of the gate because their exponents do not match. It's literally like trying to add apples and oranges. Look at the match powers step. We have to force them to share the exact same power of 10. So we rewrite that second number, shifting its decimal one place to the right, which turns 3.28 into 32.8 and logically drops its power down to 10 to the fourth. Boom, now they match. So we simply add the base numbers, 5.123 plus 32.8, to get 37.923 times 10 to the fourth. But wait, do you remember our golden rule from a minute ago? We need a single digit from 1 to 9 at the front. So for the final formatting step, we slide that decimal one spot to the left, which boosts our exponent back up by 1, leaving us with a beautiful, mathematically proper final answer, 3.7923 times 10 to the fifth meters.
Now subtraction works the exact same way. Let's analyze this next problem. We've got 10 to the negative 2 and 10 to the negative 3. Once again, we've got to match them up. We convert that second term to match the negative 2 exponent by shifting the decimal to the left this time, which gives us 0.343 times 10 to the negative 2. Now we just subtract our front numbers. 2.57 minus 0.343 gives us 2.227 times 10 to the negative 2 millimeters. But class, watch out for the final twist here. The source material pushes us one step further by converting the final unit from millimeters to standard meters. Since there are 1,000 or 10 to the third millimeters in a meter, we adjust our exponent by subtracting 3. That brings our final absolute result to 2.227 times 10 to the negative 5 meters. Really excellent work there.
All right, let's move right along to the final section of our syllabus. We've conquered adding and subtracting. Now let's tackle section 5, multiplying and dividing, and how we manage those exponents.
I really want you to notice the pure elegance of multiplication here. Unlike addition, you do not need to match the powers first. It's a real time saver. The rule is wonderfully simple. You just multiply the front coefficients together and then you add the exponents together. Just look at the calculate step. 4 times 6 is 24. Easy. And for the powers of 10, we just add 3 plus 6, giving us 9. So our raw result is 24 times 10 to the 9th. But as you know, we run a strict classroom here, and 24 clearly violates our 1 to 9 rule. So we format the final answer by bumping the decimal one space to the left, which adds 1 to our exponent and finishes perfectly at 2.4 times 10 to the 10th.
And let's wrap up our calculations with division, which is really just the inverse of what we just did. To divide, you simply divide the front numbers, and then you subtract the bottom exponent from the top exponent. In our example here, 6 divided by 2 gives us 3. Simple enough, right? Now for the exponents. We have a 6 on top and a negative 2 on the bottom. So that's 6 minus negative 2. And as we all know, subtracting a negative is the exact same thing as adding. So that becomes 6 plus 2, which gives us 8. Our final answer here actually requires absolutely no reformatting because the front number is exactly 3. So the result is just 3 times 10 to the 8th meters. A perfectly clean calculation.
As we wrap up this masterclass explainer today, I want to leave you with a bit of a provocative question to chew on. Without scientific notation, could we ever truly comprehend our place between the vastness of the cosmos and the tiny complexities of the quantum realm? Think about